If you have a reaction at equilibrium, you can make changes to throw the equilibrium off, but the reaction will restore equilibrium by shifting either left or right. Suppose that you add some NH3 to this reaction. This is a synthesis reaction of ammonia. It is creating NH3. So adding NH3 will shift the reaction to the left, or away from the change, away from the addition. So adding NH3 will cause the reaction to create less NH3 and actually create more N2 and more H2. But because you added NH3, then it will create less NH3. This is considered to be a left shift because you added something that was on the right of the equilibrium arrows, which would be here. If you remove some NH3 from the reaction, then it'll shift toward the right in an effort to replace the removed NH3. This means that the amount of N2 will decrease in an effort to make more NH3. The amount of H2 will decrease also, and it'll make more NH3 to replace the removed NH3. Now, if you make a change that involves a reactant, say you add some H2, if you add H2, it'll shift toward the right. As a result, you'll get more NH3, and then the addition of H2 will cause the H2 to be consumed faster, causing its pressure or concentration to decrease along with that of N2. Say that you remove some N2. If you remove a reactant, then that effectively slows the reaction down. It's as if you're baking cookies and someone comes in and steals some of your flour. It'll slow the reaction down, shift it toward the left. As a result, the reaction will respond by increasing the amount of N2, increasing the amount of H2, and because you removed something that the reaction needed as a reactant, it will take some time to replace the NH3, and the NH3 concentration, or the NH3 amount, the pressure in this case since it's gas, will decrease. This reaction is exothermic, which means it produces heat. This reaction produces heat just like it produces NH3. So we're going to rewrite this reaction and show heat for this exothermic reaction in the equation. Remember that the negative sign that was there when we had it in the alternate way simply means that it was an exothermic reaction, but there's a plus sign here, and the heat is on the product side because we are producing heat. Now we have this reaction at equilibrium, and we heat it up. We increase the temperature. If the temperature increases, what will happen to the reaction? Will it shift toward the left and create more reactants, or will it shift toward the right and create more products? This reaction is exothermic, which means that if you increase the temperature, it's going to shift toward the left. And that's the same reason behind increasing the amount of NH3. If you add NH3, like we did right here, then the reaction shifted toward the left because you added something that was being produced. The same applies here. An increase in temperature will cause the amount of NH3 to decrease. It'll cause the amount of N2 to increase because you're running the reaction backwards, and you're going to cause the amount of H2 to increase as well. You are slowing the reaction down by increasing the temperature for an exothermic reaction, If you think of it as a personality, this reaction does not want any extra heat. That's why it's producing or getting rid of the heat exothermically. So you adding heat will slow it down. If you decrease the temperature and you cool the reaction off, then you're making room for the addition of more heat, and the reaction will speed up or shift toward the right. And that's going to be a right shift. The amount of NH3 will go up. The amount of N2 and H2 will both go down. If you're trying to create as much product as possible, you would want to cool this reaction off so that it shifts toward the right. The next change we're going to make is volume. Let's count up how much space this reaction takes up on the left by determining the number of moles. On the left side of this reaction, we have 1 plus 3, which is a total of 4 moles of gas. On the right side of this reaction, we have just 2 moles of gas total. This means that when this reaction runs from left to right and it creates product, the products actually take up less room or less volume than the reactants. If I have this reaction taking place in a container where I can change the volume and the pressure, if I decrease the volume, a decrease in volume, as you know from Boyle's law and the gas laws, is a corresponding increase in pressure. A decrease in volume means that this reaction has less room to take place, so it's going to shift toward the side that takes up less room. A decrease in volume will shift the reaction toward the right, because the right side of the reaction only takes up 2 moles of space, and the left side of the reaction takes up 4 moles of space. Which means that you actually increase the amount of ammonia that you create. Consequently, if you increase the volume, which is a decrease in pressure, then that will shift the reaction toward the left, and it will slow it down, which means that the amount of NH3 you make will decrease because the reaction has room to expand, and it will expand into that 4 mole option versus the 2 mole option as far as which side of equilibrium it's going toward. Let's use this very roughly drawn table to determine what will happen with this reaction if it's at equilibrium and we make some changes. If we add calcium carbonate, then the reaction will respond by decreasing the amount of calcium carbonate, shifting to the right, and increasing the amount of calcium oxide and carbon dioxide that is produced. If we remove some CO2, then the reaction will respond by shifting toward the right, consuming some calcium carbonate in order to produce more calcium oxide and carbon dioxide as a result. If we remove calcium carbonate, then the reaction will shift to the left, which will increase the amount of calcium carbonate, decrease the amount of calcium oxide, and decrease the amount of carbon dioxide. And it makes sense that the amount of product will decrease because we removed some of the reactant which is used to make the product. Remember that this arrow here is not the change you made, but it's the response of the system. Because you removed some calcium carbonate, the system has to respond by creating more. If you add heat, we can see that this reaction is endothermic. So adding heat is a good thing in order to shift the reaction toward the right. This reaction needs heat to be added because it's endothermic in order for the product to be created. So the addition of heat will cause the amount of reactant to decrease, it'll shift the reaction toward the right and give us more products. If we were to remove heat, it would do the opposite. It would slow the reaction down because this reaction needs heat because it's endothermic. Removing heat slows it down. If we increase the pressure, this is the same as decreasing the volume. Increasing the pressure would shift this reaction. Increasing the pressure is just like decreasing the volume, and it'll shift toward the side with fewer moles of gas. The left side of our reaction has 0 moles of gas. The right side of our reaction has 1 mole of gas, which means that an increase in pressure will shift our reaction to the left in order to take up less room. And that means that we'll have more calcium carbonate, less calcium oxide, and less carbon dioxide. Increasing the volume is the opposite of increasing the pressure. Increasing the volume is a decrease in pressure. When you increase the volume, it allows the reaction to create more gas. So it'll increase the amount of carbon dioxide, increase the amount of calcium oxide, and decrease the amount of calcium carbonate. Some things to watch out for when you're doing Le Chatelier's principle and equilibrium shift predictions is the pressure increase or decrease only matters when there is a gas present. If the number of moles of gas are equal on the left and the right, then the increase or decrease in pressure or volume will not matter. And if there are no gases present at all, then the pressure and volume change will not matter. However, for a reaction that has an aqueous solution, increasing the concentration of something that is aqueous is just like increasing the amount of that particular thing. Suppose you have this hypothetical reaction, aqueous AB plus aqueous CD yields an equilibrium, solid AD plus aqueous CB. If you increase the concentration of AB, that's what these brackets mean, as you remember from learning about molarity. Those square brackets around a solution means the concentration or the molarity of that solution. If you increase the concentration of AB, it'll shift the reaction toward the right. If you decrease the concentration of CD, it'll shift the reaction toward the left. Now let's think about what happens when you increase the concentration of AB. Increasing the concentration of AB is like adding more AB. It will shift the reaction equilibrium away from the increase because now it has more reactant to create more product. The removal of CD should slow the reaction down because it needs CD to make AD and CB. So removing CD will shift the reaction equilibrium toward the left. Adding AD will shift the reaction equilibrium toward the left, and removing AD will shift the reaction equilibrium toward the right as the reaction tries to replace the removed AD. From these reaction shifts, you can determine whether the relative amounts of AB, CD, AD, and CB will increase or decrease.